For the chi-squared test, it is a significance test, except it considers multiple categories. At one time. So it won't be just comparing one thing, it will be comparing across multiple categories. The degrees of freedom is categories minus 1. It's not really an n minus 1 for degrees of freedom. It's however many categories you are minus 1. The last table that we really haven't used yet is table C. It's got a little x squared up in the top corner that will give you your p-value. So it's the same type of thing where we're going to reject or fail to reject. And you'll notice it's skewed data. So the picture kind of looks something like this. And the reason for this is because you're going to be using positive numbers because you're going to be using an x squared value throughout this. So it's not like you have two tails or anything like that. The chi-square test will be giving you the value to the right. So I wanted to put skewed here. Conditions. You want to make sure you're using random data. Independent is that 10% rule. For this one, we're not going to see whether it's bigger than 30. We're going to see if the counts are greater than 5. Because across multiple categories, we want to make sure the counts are greater than 5. If they're not, it's possible we might need to combine categories, if it makes sense. And we'll see what happens when we have to do something like that. The big idea for this is that it's all dealing with counts. So the actual equation sometimes looks a little like that. That's that chi-square test. And it's the sum of the observed minus the expected squared divided by the expected value. So that we're only going to be dealing with positive values. If you expect to get 15 red jelly beans, and so just think of it that way, and you get 15, you observe 15 jelly beans, when you divide this, square and divide by the expected value, you're going to end up with 0. So if there's no change between the observed and the expected, you're going to get a 0. If there's a big change, you're going to get a number greater than 0. It's always going to be positive numbers because you're going to be squaring whatever it is. And when you look at the chart, you're looking for the degrees of freedom and the chi-squared value that you end up with. And then it will give you a p-value, or you might end up with a p-value range to be able to figure something out and reject or fail to reject. So let's try a problem. According to the 2000 census of all U.S. residents aged 20 and older, 19.1% are in their 20s, 21.5% are in their 30s, 21.1% are in their 40s, 15.5% are in their 50s, and 22.8% are 60 and older. The table below shows the age distribution for a sample of U.S. residents aged 20 and older. Members of the sample were chosen by randomly dialing landline telephone numbers. Do these data provide convincing evidence that the age distribution of people who answer landline telephone surveys is not the same age distribution of all U.S. residents? So before I give the table of the counts, I'm going to use that on the next page. Your HO and your HA, your null hypothesis and your alternative hypothesis. The other ones we're all using p-values. For these ones, we're going to say it kind of in words. Like, we are assuming always that this is correct. So that's why whenever we do our rules or anything, we always use the HO to see if they fit the conditions. We'll check the conditions in a minute. Our null hypothesis is we want to assume that they are the same age distribution. So the age distribution of people who answer landline telephone surveys is the same as the U.S. resident age distribution. And for our alternative hypothesis, we would be saying is not the same. So the same type of question or statement is not the same as U.S. You get the picture. Resident age distribution. Okay, let's check the conditions to make sure that we can do that. Now, what we're going to have, like I was saying before, is this is all about counts. So here's my table of the counts from that survey. So let's also add in what we would expect to receive. So this is going to be my observed count. What's my expected count? And we might need a total here. 1048 total. Now, on the last page, 20 in their 20s was supposed to be 19.1%. So our expected count is going to be 19.1% of 1048. Or 0.191 to 200.168. Now, can you have 200.168 people? No. But we're not going to round our expected counts because it will change our answer. This is our theoretical expected count, so it doesn't have to be a whole number because we are talking about whole people. So keep the expected counts as maybe 3 decimal places, something like that. People in their 30s, it was supposed to be 21.5. So 0.215 times 1048. 225.32. In their 40s is supposed to be 21.1. 221.128. In their 50s, it looks like it is 15.5. $16244. You don't have to show the work for every single one on how to get the counts, but you do have to show the counts. 22.8. $238.94, something like that. So this is what you would expect it to be. So this is called a chi-square. This is a goodness of fit test. and you start with your x squared, and you're summing your observed minus your expected squared over your expected. And if it doesn't vary too much, it's going to be 0 or close to 0. If it varies a lot, it's going to be a bigger number. So a lot of times we'll put that x squared, and then let's start doing some calculations. So 20-year-olds, we would observe 141. We would expect to get 200.168. Square and divide by 200.168. Add it up and add it to 186. $17.49. The next one I got 6.86. Got a very small number for the second one, so this one doesn't vary too much at all. 14.52 and 9.27. And when I summed all of them together, I got 48.177 as my value. 5 categories, take away 1 is 4, and then I'm looking for an x squared value of 48.177. So we need that last little chart in the book. DF is 4, and I'm looking for 48. Ooh. It is really, really, really small. So I'm getting smaller than 0.0005. Was it random data? I'm up at the top here. Did it say somewhere that they were chosen by random? Yes. Was it independent? Which is still that 10% rule. Yes, I'm assuming that there's more residents than 1,048 or 10 times that much. Now, for this sample size, we have to make sure that the counts are greater than 5. It's got to be the expected counts are greater than 5. So when you look at our expected counts, they're all almost 200. So that definitely works as well. And that's another reason why you have to have all of them listed, is because you're trying to also check the condition as well. Component is another vocabulary word for this chapter. And when we were looking through this x squared line, when we see like 17.49, this is one of the biggest components that's making up that big 48.177. If you look at the other ones, like this one in particular, 0.037, is not really contributing too much. It's not that much different. But the biggest components are like the 17 and this 14.52, because it's talking about these are the individual components all being put together. So component is another word that we will also talk about later.